So I'm going to talk about the group of diffeomorphisms, but the real-analytic diffeomorphisms. And so I should talk about real-analytic diffeomorphisms, but first I begin with a theorem by Herman. And and it was published in 1974. And I think it is the proceeding of the colloquium held at Dijon. Dijon in 1974, yeah, and published in 1975 by Springer lecture note. And there, I just write one phrase theorem. So I'll explain all these things immediately, but diff omega Tn 0 is a simple group. Okay. So I think before theorem, the manifolds are always real-analytic or algebraic. So but anyway, Tn is the n-dimensional torus. And it is also a very well-known Lie group. And this is Rn over En. And so this part is okay. So we all learn that it is a manifold, n-dimensional manifold. So you can think about the diffeomorphism of Tn to itself. And then the diff omega this one is the group of real-analytic diffeomorphisms. And and this real-analytic is written as omega here. And what is real-analytic? I don't know whether you learned what is a real-analytic mapping in the course. So, but here we have the torus, and this is the quotient space of Rn. We have very nice local chart, of course, Rn itself. And then, so the element f here, f should be written as x1, xn to be f1 of x1, xn, fn of x1 to xn. And all these are the function from the Tn to real, but modulo z. So you can think of the lift of the map, which is coming from Rn to itself. And these Fi are real-analytic. And real-analytic means, so if you have at least C infinity, and Fi are C infinity, and at every point, x, you will have Taylor series expressing this Fi. Fi, how do you say? Every point x0, x minus x0 should be written as a I of x minus x0 I, and I should be I think 0 to the n. So you will have this kind of Taylor expansion. Okay, this is what they say, the multi-index. And you just think one-dimensional case. It will be enough later. So, and then this is just a convergent series. So, no, not yet. And this is C omega. If these series are convergent, is it clear? And I think maybe it should be good to know if you have a C infinity map with so there is inverse mapping theorem. And usually, if df is invertible at x, there exists G from some neighborhood of f of x to u of x, such that it is inverse map. So fg equals the identity at u f x, and gf is the identity at u of x. Okay? And I think we learned in many places that if f is C infinity, then G is C infinity. And you may try to prove that if f is C omega, then G is C omega. It may be clear for you. Yeah, you can, but with this definition, it is not so clear for me. Yeah, please.
I used to think that analytic map is such that say it does not only converge, but converges to F.
Not only converge, but converge to F. You're right. Of course, yeah. I hope so. Convergent. Converge to F. Right. Is there another thing I should correct? I mean, it's okay. So you can think of the diffeomorphism that told us real-analytic diffeomorphisms. These are the homeomorphisms and differentiable, infinitely many times differentiable, and also its Taylor expansion is converged to itself, and also its inverse as well. Okay. So I explained what is C omega, and I need 0. So what this diff omega t and 0. This 0 means is the connected component of diff omega Tn of the identity with respect to CR topology for R, I think it's necessary to greater than 1. And I think all these topology induced on that one space should define the same component. Yeah, it's a kind of I think, good exercises. And a group is simple. All of you know, I think. A group G is simple if there are no regular subgroup other than the trivial one and G itself. The all of H G, this means regular subgroup. So if in, then H equal only the identity or G itself. But this definition is not really useful. So if you have, this is the same thing as take f of G, and then also f not identity, and G anything. There exists the finitely many H1, Hk, such that G is the product of the conjugates H1 F plus minus H1 inverse H2 F plus minus H2 inverse HKF H inverse, and F plus is F itself, and F minus is the inverse of F. So if it is said, then if there is some subgroup which contains F, then any element is in its normal closure, what we call. So this statement, in fact, we should prove for this group. That is the Herman theorem. I said, okay. But even Herman cannot prove without any any result obtainable at that time. And the most important theorem at that time was a theorem by Arnold. Much before 1960 something, I think. And so it is stated, so we take alpha of the real number, and we assume that alpha is Diophantine, and another name of Diophantine is badly approximable by rationals. And that is, this is a vector. So for any k of the n, any L of z, k alpha minus L, I think, is so if it is very small, it is approximated. This, at least, this inner product is approximated by rational. So I want to say that this is, even if I divide by L, it is bigger than L of some number. And plus epsilon, something like this.
That be A.
What?
Should that be A instead of L on the right side?
Should that?
On the right hand side.
The last L is in
Maybe I should look at my note. Oh, my note doesn't give me the good answer. Something, so I want to, in the low dimensional case, I want to write something like P over Q. If it is in real, is bigger than P to the 2 or 3, some plus epsilon or something. Yeah. And then, so this P, oh, okay, you are right. Thank you. Maybe the index is wrong. Okay. So the theorem of Arnold is not this definition. And what he proved is that, so for any, we have alpha is Diophantine. We have the rotation by alpha on n over Zn. And we take f near alpha and fc omega, and we can define a kind of rotation number. It is only defined for the, in some small neighborhood of this rotation if the dimension is high. In the one-dimensional case, we know that for any diffeomorphism of the circle have the rotation number. They are the same. And if the rotation number of some element very close to this rotation is this alpha, then there exists h c omega diffeomorphism, and f h inverse is R alpha. So it is very interesting to know why Arnold thought of such questions, and it should come from the celestial mechanics, the existence of the invariant torus. Even if you perturb, it resists. So they thought about that thing, but anyway, he proved that. So how Herman proceed? Is there any question? Yes, please.
Is near the rotation the analytic distance?
I didn't define analytic distance, and I said C1, C2, C. So the topology here is, yeah, here, still there. And I'm thinking CR topology for R greater than 1, always. Okay? Yeah. There is, I think, yeah, you are right. We should think about the C omega topology. What? Anyway, I hope I didn't So what he thought there, he begins, Herman begins with some simple observation. So anyway, we can think about rotation alpha. And this rotation, F might be near, but if you allow F is arbitrary, this condition might not be satisfied. So even this case, for small t, you can think of this kind of the consideration on Tn. You know that PSL to R act on the circle. Okay, no problem. So on the torus, for each coordinate, PSL to R can act. And then act. Yes. So, and moreover, so PSL to R itself is simple. Okay? You can prove by writing down the equation. So since it is simple, we can have, this can be written as a T of one element G and a T inverse and BT G inverse of BT inverse. Where these AT, BT are all G, BT belongs to this group. It is easy. So I need another, this is already big theorem, but I need another big theorem. So, well, I should remember, I hope somewhere psi exists still. No. G is simple. So I want to show that something is simple. So I will take F. Diff of omega of Tn. This is my group. And I want to write down this way. And then, so there is a theorem by who should I? Mother certain Herman. Yeah, this is in the Thurston's paper in the bulletin. Foliation is the group of diffeomorphisms, I think. That this group, if it is not C omega, diff infinity Tn 0 is simple. And then I don't prove this, sorry, but and because of that, this G, this is surely an element of the PSL2R. Yeah, I can show this part very easily, but anyway. So G can be written so maybe better to write in the same way as that. H1 F plus minus H1 inverse HKF plus minus HK inverse, where HI's are the infinity of Tn 0. This is just, I rephrased this one for a very special element. So, and then there is important thing. Diff omega of some any manifold is dense in diff infinity of M. I should be happy to prove this one, but I prove first these things. And then, so this is a fact. Since it is dense, I can change this thing H1 to HK by its approximation in diff omega. So let HI tilde be an approximating element in diff omega of HI. So I formed I can form the same thing to obtain some element near the first G. So let G tilde be, so this one, H1 tilde, F1, no, F plus minus, H tilde inverse, HK tilde F plus minus H K inverse tilde. So this is now the diff omega of Tn. But and okay, no problem. So what? So now I have this G tilde, and there is some formula there with G. So I'll look at AT of G tilde, AT inverse, and BT of G tilde inverse, BT inverse. This is some element. Yeah. So we look at this element. This element is C omega diffeomorphism, very near to the rotation because I approximate everything. So, as I said, in the neighborhood of this rotation, we will have the rotation number. Okay? So, in the family, in this T family, there exists T0 such that its rotation number is equal to alpha. Because, so I said it is R alpha plus T, and it is easier to think it is one-dimensional. So if the alpha plus T varies less than alpha to bigger than alpha, then this number, so even should at this rotation, at t equals 0, rotation number is just alpha. But even for this family, if this t is negative, the rotation number should be less than alpha. And if t is positive, it is bigger than alpha. So there are some t0 where the rotation number is alpha. So even if dimension is higher, if you think about rotation alpha is somewhere there, we have this neighborhood, and every point is approximated. And so if you think about the rotation number of this element, this somehow covers this point alpha. So you should have some parameter t0 where the rotation number is alpha. So this means with this alpha, AT0, G tilde, AT0 inverse, BT0, G tilde, be T0 inverse is, can I still use H? Maybe. H inverse alpha H. That is where I wrote here.
Second G tilde is inverse.
What?
There's an inverse for the second G tilde.
Oh, thank you. Thank you. So what does it mean? So here is my F. So what do I prove? I proved that R alpha is in the normal closure of F, because G tilde is something like that. This is the product of the conjugates of F or F inverse. And even if it is conjugated again, the same thing. And this is the same thing. So R alpha is in the normal closure of F. Okay. Then what? Yeah, it's good. So as I told you, PSL2R is simple. And the direct product of this n thing is not a simple group, but the fact that PSL2R is a simple group so if you look at this element and I think it's true. So it's if normal closure of F contains this one, the normal closure of F should contain. So I should write normal closure of F contains one specific rotation, then this contains PSL2R times PSL2R. In the one-dimensional case, it is evident, I think. In the multidimensional case, yeah, it should be exercised, I hope. Okay, so if you're just interested in one-dimensional case, it is, since this is simple group, if it contains one element, then it contains all. Yeah. And then, so what? So if it contains, in the subset of this one, it contains Tn, So normal closure of F contains all the rotations. But here is another thing. In order to show this theorem, theorem of Arnold, Arnold in fact showed the following. So if you have some element very near to the rotation, if you want to change the rotation number, one of the best, I think, easiest way should be so it's better to write here. In fact, so this was the first expression. In the same assumption, there exists lambda near 0 such that F rotation lambda is equal to H inverse R alpha H. I should, it is manual. You can see. So, as I said, so this theorem says if the rotation number is alpha, it is just the conjugate of the rotation. Fine. But usually it is not. So I want to change the rotation number. The easiest way is multiply the rotation. If there is big rotation, then that should obtain big rotation. So in fact there is unique lambda such that F composed with the rotation is the conjugate of this rotation. So what I told you somewhere here, yeah, the normal closure of F contains rotation, then F is contained in the normal closure of F. So this, from this in fact, this fact implies F, normal closure of F, contains there's something wrong. I'm sorry. So I used two F's. So this is normal closure of F, and what I should write here is the neighborhood, a small neighborhood of R alpha. Is it clear? So if I take some element very near to the rotation, I can, in some sense, modify its rotation number, and it will be conjugate. So this element is in fact written as the conjugates of the product of the conjugate of the rotation, and this means the given F a neighborhood of this one is contained in the normal closure of F. So we won. So once you have this open set in our group, its inverse will contain the open neighborhood of the identity. Clear? So normal closure of F contains a neighborhood of identity. And the neighborhood of the identity should generate all the connected components. So then n of F contains diff omega Tn 0. So this is a proof by Herman. Incredible, I think. And then I have maybe 5 minutes. So there are many interesting things in the proof. But one of the most important parts, one question. I think it is true, but so we use big theorem, Mother, Thurston, Herman. I think we can use the fact that diff of 1 Tn of 0 is simple. It is given by Mother. And more than that, we can give the explicit proof. If you are given some element, you can write it as a product of element supported on the open set. And after that, for example, you can write the first product of the commutators of the commutator length, maybe 6 to the n, but still some number, bounded number. And then in the proof of the simplicity, you can have some bound for this length of the somewhere. I should have to write element by h1 to the etc. to there is some k there, and this should be bounded. So I think can be used. Anyway, so this is one question. And the other thing, important thing, is the density of M or diff Rm. So for me, it was not clear at all. And then this is really Hefliger taught me one day. How do you prove? So it is, in fact, if you have a mapping Mn. It can be maybe CR. And F can be approximated by C omega thing. And proof uses the, I think we call it Nash embedding theorem for C omega manifold. So this means all these things are embedded in Rn. And I have some map. Then M is somewhere there. N is somewhere there. We have this Euclidean space. And we can extend this map F in a neighborhood. And still the image is the same, maybe. And then we approximated this F by using Weierstrass approximation theorem. You remember you learned something? So F tilde is Weierstrass approximation. But with this F tilde, the image of this M, there was M, would be a little different from the original N. But here, Nash embedding theorem is real-analytic embedding. So we have a normal bundle of F in this Rn, and we have normal bundle projection. So there is a projection. Then if you look at the composition, this is real-analytic. I'm really grateful to Andor Hefliger that he taught me this one I can use to prove the theorems. Thank you.
Questions?
Yes, please.
Is it a Nash embedding theorem? I think it's due to Gravert.
Gravert?
Yeah, I think.
Yeah, maybe. Yeah, it is also Herman wrote. It is Gravert embedding theorem. I thought always it is Nash embedding theorem, but maybe different. Yes, please.
I'm sorry, it must be the part of the theory I don't know very well, and I must miss something. So when we have a circle diffeomorphism, there is one rotation number. But if we have a torus diffeomorphism, homotopic to the identity, I have impression that it's a set rather than one vector.
Yeah, that's right.
How do you ensure that in this
Yes,
conjugacy?
you're right. And in order to show Arnold's theorem, we have to use the Taylor expansion. No. Fourier expansion. Then Fourier expansion is given f, given rotation, first of all. Then the Fourier expansion is, of course, addition. And the Fourier expansion of given f very near to that one will begin the zeroth term, one term, etc. And what is necessary after is the zeroth term correction. So you can, in fact, it is a kind of, how do you say, Newton approximation method. So there is the limit we have. And then this limit is, in fact, unique. And we define it, the rotation number, for the element near to this Diophantine rotation. It is only defined for this small neighborhood. Okay? Okay? Yeah, you are really right. So in the one-dimensional case, we are happy.
So if I follow the proof correctly, so you really don't need the full power. You just need one Diophantine vector, right?
Yes.
Just one alpha.
Yes.
Simple,
Yes. Right.
like coordination.
Yeah. That's right.
Is the commutator length of analytic diffeomorphism the same as C-infinity diffeomorphism, at least for the torus case?
In general, you mean?
No, at least for the torus case, or the cases that we know that it's perfect.
Let me, even for the circle case, I'm not sure. In the circle case, the commutator length, I think it is 2, because there is, in the C-infinity case, there is a big theorem by Herman. And if the rotation number is Diophantine, even if it is very far from the rotation, there is some element to conjugate it. But usually, using this type of the argument, we will have a very small neighborhood. And usually, we need the long, and I'm sorry, no. Yeah, it's a good question. So that's why I had this question. Yeah, they proved this one using that big theorem. Yes, and preparing this talk, I wonder why it is infinity. And I think they can do with C1 because the topology is even nice in C1. So yeah, here the commutator length is rather low. Yes.
So we established that in the second mode that the rotation which with angle alpha is in the normal closure of F, but it is true for alpha Diophantine, right?
Yes.
And how do we pass from all the finds into all angles after?
Why everything was so because first of all, we begin with the first equation, very top of that the third blackboard, and I want to just write one rotation is in the normal closure. And if one rotation is in the normal closure, then because its conjugate can write all the rotations. Okay? So something like, I don't know how to draw it. If you have some rotational element, one-dimensional case is very easy to explain. Rotational element is some translation. And if you conjugate it, you will have something like this. And if you take the conjugate and its inverse, you will get some parabolic element, for example. And you can produce a lot of elements in this way. So you can finally produce all the elements of PSL2R. So if all the elements is in PSL2R, rotations are there. That's the argument. Okay?
All right, we're a bit short in time, so let's thank Takashi again.
Thank you very much.